Namaskar friends, welcome to this video lecture series on transformers. In this session we are going to solve various examples on transformer. We will start with the simple example and gradually we will improve the level of these examples. In this session we are going to solve 3 to 4 different types of simple examples on transformers, and then at the end of the session I am going to give you 2-3 examples to solve by yourself, and that will be the question for you, but that's into the end of the session. So here we will start with this simple example, and first of all we will take our green pen and write data given. So whatever the data is given we will write over here, and the data given is find the full load primary and secondary current. So initially it has started with findings, so we will write data to find. So we need to find primary current, so we will write primary current as I1 and secondary current, so we'll call it I2. Primary and secondary current of 230 by 115 volt. See, whenever the data is given like this 230 by 115 volt, this means it is V1 by V2. So V1 that represents primary voltage and V2 that represents secondary voltage. So the primary voltage is 230 and secondary voltage is 115 volt. It means a step down transformer, right? So V1 is 230 volt and V2 is 115 volt, and the third is 2 kVA transformer. So it is the power rating of transformer. P is equal to 2 kVA. So that's all. This much of data is given to us, right? And let me draw this circuit diagram of transformer. It's a step down transformer, so there are more number of turns on primary and less number of turns on secondary. Supply voltage V1 is 230 volt and the secondary voltage is 115 volt, that is V2, or simply 115 volts V2. So this is the circuit diagram, and we need to find the current flowing through primary winding, and when we connect the load, current flowing through secondary winding. See, what is the definition of transformer, right? The definition of transformer is it will transform or it will step up or step down either voltage or current without changing in power and frequency. So transformer will not change power and frequency. Whatever power we are giving in input, if it is ideal transformer, that much of power will get at output. So the power for input P1 is equal to power output P2 is equal to total power of transformer. So this is the simple equation that we need to remember. Now we'll start the solution. For solution we need to find the current, primary current and secondary current. So the equation of power P is equal to VI cos phi. This is watt power, right? But over here the power given to us is kVA, and when we convert watt power in kVA, or simply if we write equation of power for kVA, then P is equal to V into I. So the power of transformer is 2 kVA, so P. If we want to find primary current, we will take primary voltage and primary current. So I1 is equal to P by V1. P is equal to 2 kVA. If we convert into kVA to VA, so it's 2000 VA divided by V1, it's 230. So if we calculate it, it's 2000 divided by 230 gives us 8.69. So we'll take it as 8.7. So it is 8.7 ampere of current is flowing through primary winding. Now if you want to find secondary current, this is the current flowing through primary winding. Now we are going to find the current flowing through secondary winding. So again P is equal to V2 into I2, because the power in transformer is constant. Whatever power, electrical power, is at input in ideal transformer, that much of power we'll get at output. So V2 is 115, right, multiply by I2. So if I write this equation for I2, P by V2, it's 2000 divided by 115, and 2000 divided by 115 gives us 17.39. So we'll take it as 17.4, right? 17.4 ampere. So that's it. This is how you can solve this simple example. If you want to observe this example, you can observe in this manner, right? If you have any doubt and query, you can ask me in comment section. I suggest that whenever we are going to solve the next example, you all calculate this example with me using the pen, paper and calculator, and try to answer your calculations into the comment section. So this is our example number 2 that we are going to solve in this session. First of all, we'll take our green pen and write data given. So whatever data given we'll mention over here, and we'll start with this example. The turns ratio of 10 kVA single phase transformer, that means P is equal to 10 kVA, and turns ratio means it is the ratio of primary turns divided by secondary turns. So the turns ratio is N1 by N2. 10 kVA, it's P. Single phase transformer, this is single phase transformer, 300 by 23, it is the turns ratio of this transformer. So 300 by 23. Primary winding is connected to 1500 volt, that means V1 is equal to 1500 volts primary winding. 50 hertz is supply, so the frequency is 50 hertz. Find the secondary winding. Okay, so now we need to find the data. So we will write using red pen data to find. And what data we need to find? Find the secondary winding voltage at open circuit. So in open circuit condition we need to find V2. Find also the full load primary and secondary current. So we need to find I1 and I2, right? So we will go for the solution. Let's start the solution from here. So first we need to find V2, right? And one of the equation of number of turns and voltage that we have seen over one of the previous session, right? That is N1 by N2 is equal to V1 by V2. So if from this equation we will write or rearrange this equation to find V2, then V2 is equal to N1 by V2 is equal to V1 into N2 by N1. Now let's just verify that do we have the value of V1? Yes, we have value of V1, N2 and N1. Now see, we have the ratio N1 by N2. And now if we want to use n2 by n1, we just need to invert this thing. So whatever data we require, we have all the necessary data. So just place the values 1500 multiply by 23 and divide by 300. So let's calculate this thing. 1500 multiply by 23 and divided by 300. It's simple. It gives us 115. So the secondary voltage at open circuit V2 is 115 volt. So that's it. We have found our first findings and it is 115 volt. Now we need to find the current, primary and secondary current. Can anyone just recall that in previous example we have used a very simple method to calculate current, and that is P is equal to V into I. The power is already given to us. So now if we find I1 current first, then we need to modify this equation as P is equal to V1 into I1, and then I1 is equal to P divided by V1. P is equal to 10 kVA, 10 kVA, right? And divided by V1. So where is the V1 voltage? It's 1500, right? Here it is. So it's 1500. But just imagine that this 1500 is in volts and this power is in 10 kVA, in kilovolts ampere. So what we need to do, we need to convert this kVA into VA, and for that we need to multiply it by 1000. So this will become 10,000 divided by 1500, and that will give us 6.66 ampere. So I1 is equal to 6.66 ampere of current will flow from primary at full load condition, because the full load is given to us as 10 kVA. Now go for P is equal to V2 into I2. So I2 is equal to P divided by V2. So we'll directly write this thing into VA. So 10,000 VA divided by V2 is 115, and that gives us 10,000 divided by 115. It's 86.956. So it's almost 86.96. 86.96 ampere. I2 is equal to 86.96 ampere. So this is how you can solve this example. It's pretty much easy, right? We have started with solving some easy example, and then we'll gradually move to little tricky examples. So this is your second example of this session. Just have a look to this. If you have any doubt and query, you can ask your doubt and query in comment section. And if you are ready with the next example, then let's move for the example number 3, which is little bit more trickier than this. So here it is, our example number 3. So let's begin with data given. So let's write here data given and begin with this example. So this is our example number 3. So let's start with data given. The value of maximum flux density in the core of an 11,000 by 440 volt 50 hertz single phase transformer. See, again here a voltage ratio is given. So 11,000 by 440, it's always V1 by V2. So V1, that is primary voltage, this is 11,000 volts, and the secondary voltage V2 is 440 volts. Now the next is 50 hertz single phase transformer. So F is equal to 50 hertz single phase. So 50 hertz is single phase transformer is 1.1 Weber per meter square. So what is this? This is 1.1 Weber per meter square. That represents what? The flux density of this transformer is 1.1 Weber per meter square. Maximum flux density. So we will mention this maximum flux density 1.1 Weber per meter square. Bm is equal to 1.1 Weber per meter square. If the value of primary winding turns is 5500, so primary winding turns is N1 5500. Now find cross sectional area. So we'll write data to find cross section area of core. So cross section area of core, that will be mentioned as A into I. AI is the cross sectional area of core. So we need to find this. Then number of turns of secondary winding. So the next we need to find is N2, number of turn in secondary winding. Then turns ratio. So turns ratio is N1 by N2. Then transformation ratio. Transformation ratio is mentioned as V2 by V1. And volt per turn. So 1, 2, 3, 4, 5. These 5 quantities we need to find. So let's start with the solution. So first of all, we want to find the cross sectional area, right? Cross sectional area of the core. So how we can get the cross sectional area of the core? Just remember the equation for induced EMF. The equation for induced EMF is E is equal to 4.44 F, right? F phi N1, right? This was the equation. E is equal to 4.44 F phi N1. So from here, the flux represented over here is basically a maximum flux. Flux represented over here is maximum flux. And if you remember, then the equation for flux density Bm is equal to phi m by Ai, cross sectional area. So instead of this phi m, if we replace this equation Bm into Ai, then the equation for induced EMF will be modified as 4.44 F Bm Ai N1, right? So this is the equation of E. Instead of E, if we write this equation for V1, right? So V1, the equation for V1 will become this. So now let's place the values and find the AI, cross sectional area. AI is equal to V1 divided by 4.44 F Bm N1, and V1 is primary voltage, that is given as 11,000 volt. So primary voltage is 11,000 volts. divided by 4.44. Frequency is 50 Hertz, and BM maximum flux density is 1.1 Weber per meter square, and N1 primary numbers of turn is 5500. So from this, if we calculate AI, then 11,000 divided by 4.44 divided by 50 divided by 1.1 divided by 5500 gives us 0.00819. 0.00819. So this will be the area of cross section, right? So 0.00819 meter square will be the area of cross section of core. The next important quantity that we need to calculate is N2, number of secondary turns. And how we can calculate number of secondary turns? The equation we remember that V1 by V2 is equal to N1 by N2. We want to find this. Do we have the value of primary number of turn? Yes. Primary voltage? Yes. Secondary voltage? Yes. We know all these three quantities. So it's simple to calculate N2. N2 is equal to N1 multiply by V2 by V1. N1 is 5500 multiply by V2 440 volt divided by 11,000. And now if we calculate this, 5500 multiply by 440 volt divided by 11,000 gives us 220, right? So number of secondary turns will be 220. N2 is equal to 220 turns. So this is our second finding. The third thing which we need to calculate is the ratio N1 by N2. So it's very simple to calculate. The N1 by N2 ratio is 5500 divided by 220. And if you want to simplify it, you can write 25 by 1, right? Because you can do this. So 220, 55, 100 divided by 220 gives us 25. So we can write the ratio as 25 jam 1. Now the next thing we need to calculate is V2 by V1, transformation ratio. And transformation ratio is known as V2 by V1. The secondary voltage is 440 and primary voltage is 11,000. So it's 440 divided by 11,000, and this gives us 1, 2, 3 zeros. Let me do it like this. So 0.04. So this ratio is 0.04 by 1. So we have got the transformation ratio, we have got the number of turns. At last we need to find volt per turn. So what is basically volt per turn? So from this equation, V1 by V2 is equal to N1 by N2. Just write this equation, V1 by V2 is equal to N1 by N2, and rearrange this equation as V1 by N1 is equal to V2 by N2. So this is known as volt per turn. So any of these you can use, right? So we will use V1 by N1. V1 is 11,000 and N1 is 5,500. So this gives us 11,000 divided by 5,500 gives us 2, and it is very simple to calculate. So 2 volt per turns. So volt per turn is 2 volt per turn. So this is how you can solve this example. It's pretty much simple example. Just go through this. If you have any doubt and query, you can ask your doubts and queries in comment section. And now we'll move for the another example. And this is our final example of this session. So for this we'll write data given, and we'll start with the example. The flux density of 250 by 3000 volt, so it's V1 by V2. So V1 is 250 volt and V2 is 3000 volt. Frequency F is 50 hertz, single phase transformer. So the flux density Bm is 1.2 Tesla, right? So the flux density Bm is given Bm is 1.2 Tesla. If the EMF per turn is 8 volt, so it is new thing, EMF per turn is equal to 8 volt, then find. So now we'll write, we'll go for data to find. And what data we need to find? Find numbers of primary winding turn. So we need to find N1, then numbers of secondary winding turns, and 2, net cross section area of core, that is AI, gross cross section area of core, so that is gross cross section area of core. So this is these are the 4 quantities that we need to find. So let's start the solution. So first of all we'll start with the equation of this net cross sectional area, because we have one equation, Bm is equal to phi m divided by AI, right? So flux density Bm, that is given 1.2 Tesla, but phi m, that is not given. If we have this value of phi m, then we can find AI very easily, right? So what is our first task? Now our first task is to find phi m. So what equation do you remember which includes phi m? And the equation that includes phi m is E is equal to 4.44 F phi m n. So this is the equation from which we can find the phi m, but over here it is n, its number of turns. If we are finding the voltage in primary, then primary numbers of turns, and if we are finding the voltage in secondary, then secondary numbers of turns. But in this case we need to find both these things. We do not know the value of n. So now what to do? Now use the data given over here, EMF induced per turn. So now we will use EMF over here. It's not the total EMF that we are going to use in this equation. We are going to use EMF induced in 1 turn. So how much EMF is induced in 1 turn? It's 8. So we will take n is equal to 1. and E is equal to 8. So our equation will be modified as n will become 1 and this is given as 8. 4.44, f is equal to frequency, which is 50 hertz, and now we can find phi m easily, right? So multiply by phi m, multiply by 1. So phi m is equal to 8 by 4.44 into 50 into 1. So let's calculate this thing. 8 divided by 4.44 divided by 50 gives us 0.0360. So phi m is equal to 0.0360 Weber. So 0.0360 will be the flux. Now if we use this value into this equation, then Bm is equal to phi m divided by Ai. So we want to find for Ai, phi m we have just found over here, and Bm is already given. So Ai is equal to phi m divided by Bm. Phi m is 0.0360 and Bm, that is 1.2 Tesla. It is ultimately Weber per meter square. Tesla is equal to Weber per meter square. So it is 1.2. So this is divided by 1.2 and gives us 0.0300. So Ai will be 0.0300 meter square. So this will be the net cross sectional area of the core. Now if we want to find the gross cross sectional area, that is known as Ag, right? So one of the equation is net cross sectional area is equal to gross cross sectional area multiplying by stack factor, and the stack factor we will know as Ks. Generally we assume this value near about 0.9. So in this example we will assume this stack factor as 0.9, and from this equation we can write Ag is equal to Ai divided by Ks, or 0.9. Anything you can write. Ai is 0.0300 divided by 0.9. So Ag is divided by 0.9 gives us 0.0333. So let's write it over here. Ag is equal to 0.0333 meter square. So this will be the gross cross sectional area of the core. Now we want to find the N1 and N2. So to find this thing, we have the equation N1 by N2 is equal to V1 by V2. So the value of primary and secondary voltage we know, but none of this quantity we know. We don't know V1, N1, and we don't know N2. So now how can we find this N1 and N2? From this data, again we are going to use this thing. See, EMF per turn. So what is EMF per turn? Let me write over here. This is EMF per turn. It's ultimately EMF by turns ratio. So V1 by N1 ratio. And the value of EMF per turn is given. The value of N1 that we know, that is 250. So we can easily identify or calculate N1. So N1 is equal to V1 divided by EMF per turn. is equal to 250 divided by 8 gives us N1 is equal to 250 by 8, 31.25. Either turns can be 31 or it can be 32. It cannot be 31.25, right? So we will round about it and roughly will take it as 31 turns. So we'll get the N1. Now this three quantity we know, and from this equation if we write equation for N2, then N2 is equal to N1 into V2 by V1. N1 is 31, V2 is 3000. So 31 multiplied by 3000 divided by 250. So N2 is equal to 31 multiplied by 3000 divided by 250. So it's 372, right? So N2 is 372 tons. So this is the final example how you can solve this thing. Just have a look of this example. If you find any doubt and difficulty in this example, then you can ask me in comment section. And now finally we are moving towards the question for you session. So let's move. So these are the two questions which you need to solve. These two examples you need to calculate and you need to write the answers of these examples into the comment section. If you find any difficulty during solving these examples, you can refer our previous example solution and you can solve your difficulties. If you still find any difficulty, then you can directly commenting into this video and contact me, and I'll get back to you and try to solve your comments. Your doubts. So please solve this and write the answers of these questions into the comment section, right? So until you watch our another video, till that time, bye bye.